Welcome to Lesson 2.5, Scientific Notation. Today we're going to talk about converting large numbers to scientific notation and very, very small numbers to scientific notation. We're going to determine whether an exponent should be positive or negative based on the number in standard notation. Determine if a number should be greater than or less than 1 based on the exponent. And we're going to convert numbers from scientific notation to standard notation and compare numbers in scientific notation. All right, so to start off, we need to know what scientific notation is. Scientific notation is a method of expressing very large and very small numbers as a product of a number greater than or equal to 1. So it's a product of a number greater than or equal to 1 and less than 10. Okay, and a power of 10. So I'm highlighting here, and I'm actually not going to highlight product. I'm highlighting that it has to be greater than or equal to 1 and then less than 10. Okay, so for example, you have 2 and 946 thousandths times 10 to the 12th power. So if we had written out this number in standard notation, it'd be very, very, very long. And you have 7 and 63 hundredths times 10 to the negative 14th power. Again, this number would be very long if we had written this in standard notation. Again, your base is the number being multiplied. Okay, in this case, your base is the 10, and your exponent is the small number that tells the exponent how many times to multiply, or I'm sorry, the base how many times to multiply itself. So in this case, the 12 and the negative 14. So when we talk about scientific notation, your base is always 10. And then your exponent is the same thing. So it's going to be either positive or negative, and it's telling you how to move your decimal and whether to multiply or divide. All right, so let's go ahead and get started. When using scientific notation, you're looking at numbers that are very big and very small. In this case, we don't have that large of numbers, but we're using smaller numbers to get used to the idea of scientific notation. Okay, so we have the weights of various sea creatures, and we're going to write them in scientific notation. So what I have to do is I have to look at my numbers. So I have 250,000. And my first number has to be a number that is between 1 and 10. So it can be 1, but it cannot be 10. Okay, so looking at this number, to make a number that's between 1 and 10, I would have to put the decimal between the 2 and the 5. So to do that, I do 2 and 5/10, and I put my decimal there. And I know I have that little dot there. We'll go ahead and get rid of that. Okay, and then it's a product, so I'm going to multiply. Now, I know that what I did is I took my number and I moved the decimal 1, 2, 3, 4, 5 places to the left. So this would be times 10 to the 5th power. Because what this means is going to happen is that I'm going to take 2.5, and if I multiply it by 10 to the 5th power, which is 1 and 5 zeros, I know from previous math classes that when I multiply by a power of 10, what is happening here is that I'm being told to move my decimal the number of places that I have zeros. So in this case, I move it 1, 2, 3, 4, 5 places to the right. So if I do that, 1, 2, 3, 4, 5, 1, 2, 3, 4, my number turns back into 250,000. Okay, so this is just a general explanation of what's going on. Basically what you're doing is you're saying, okay, I need to move my decimal to make a number that's between 1 and 10. And then once I do that, I have to figure out how many times I moved it, and that becomes my exponent on my base of 10. So let's look at the whale shark. The whale shark is 41,200 pounds. I move my decimal 1, 2, 3, 4 places, and it becomes 4 and 12 hundredths, because I can get rid of any of the zeros as long as they're at the end, times my base is always 10, and I moved it 1, 2, 3, 4 spaces. Now, the reason that the exponent is positive is because when I change it from scientific notation, I want the number to be greater than 1. I want the number to get bigger, so I need to have a positive exponent. Here, we're going to look at the minnow, and we have 0 and 95 hundredths. In order to make a number that's between 1 and 10, I move my decimal one place to the right, and I get 9.5 times my base is 10, and I moved it once, but since I moved it to the right, it's a -1. Because then what that -1 tells me is that when I change this back, I'm actually going to move it to the left one place instead of to the right. So positive exponents tell us to move right, and that we're multiplying by the power of 10. Negative exponents tell us to move left, and that we're actually dividing by that power of 10. So we're going to talk about in a little bit how this connects with what we know about negative exponents. All right, so to translate between standard notation and scientific notation, like we said, we have to count the number of decimal places. Okay. When the number is greater than or equal to 1, we use a positive exponent. So in this case, because 84,000 is greater than 1, my exponent is positive. When my exponent, or when my number is less than 1, my exponent is going to be negative. And we've talked about this before. We know that negative exponents turn the number into a decimal. Well, actually, we should say into a fraction. And we know fractions can turn into decimals. Okay, so whenever I have a decimal, I know that my exponent should be negative. And we've talked about that previously in terms of laws of exponents. So now what we're saying is whenever I want to turn a number into scientific notation, 10 is still going to be my base, but I know my exponent has to be negative because I want my number to turn back into a decimal. I want it to turn back into a number that's less than 0. Okay, so when we write a number in scientific notation, we have to look at the problem. In this case, we have an estimate of the world population. Okay, so it's 6,880,000,000. And we're going to write that in scientific notation. So the first thing I do is I place the decimal point. So here's all of my numbers, and right now my decimal point is at the end. And I want to make a number that is, so my number has to be greater than or equal to 1, but less than 10. Okay, to do that, my decimal has to go here between the 6 and the 8. Okay, because I only want one number in the front, and I want it to be between basically 1 and 10. So now I need to figure out which direction did I move my decimal point. I moved it to the left. Because I moved it to the left, or let's count how many places. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I moved it 9 places, and the number that I found was 6 and 88 hundredths, because then what I do is I just get rid of all these extra zeros at the end. Okay, so to write this in exponential, or I'm sorry, in scientific notation, I use how many places I moved my decimal to figure out my exponent. So here, the exponent of the power of 10 should be 9. And so I take my new number, which I said was 6 and 88 hundredths, and I take that times 10 to the 9th power. Okay, so now I know that based on this, if I want to double check my answer and make sure that my exponent seems right, I know that if I take this small number times 10 to the ninth, I know that it's going to make my number larger because of the fact that my decimal is going to move to the right. Okay, so since my decimal point moved left, my exponent has to be positive. Okay, so let's go ahead and try this. So these you have to write down on your own. So I have 58,927. I know the decimal always starts at the end, so I'm going to move it 1, 2, 3, 4 places, and I make 5 and 8,927 ten thousandths times 10 to the, well, I moved it 1, 2, 3, 4 times, times 10 to the fourth. Here I have 1,304,000,000. And instead of writing out all these zeros, I want to shorten it. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I know that it's going to be times 10 to the ninth, because that's how many places I moved my decimal. And this number, since it's greater than 1, my exponent should be positive. And the number that I created, I have to keep this 0 between the 3 and the 4 because it's a placeholder, but I can get rid of all these zeros at the end. Now, one thing that I do caution you on is students like to count like this. They go 1, 2, 3, 4. You don't count the comma. The comma is not a place value. It's just showing you that you're moving to the next chunk. So do not double count those commas. Okay, now we have a number, so 487. So we have 487, and this is thousands, 10,000s, 100,000s, millions. So this is 487 millions. Since this number is less than 1, I know my exponent is negative because I want my exponent. So when I turn this into a number that is greater than 1, so 1, 2, 3, 4, so I turn this into 4 and 87/100ths. When I take it out of scientific notation, I want it to go back to being a decimal, so I know it has to be a negative, and since I moved it 4 times, it's a negative 4. Okay, and one more, so I have 0 and 417 ten thousandths. Again, so since it's less than 1, means it's a negative exponent. I move it 1, 2 places to the right, so this is 4 and 17/100ths times 10 to the negative second power. So I still count how many places I move the decimal, but the negative tells me which way I'm moving that decimal. Okay, and since my original number was less than 1, my exponent should be negative. Right, so converting from standard notation, from scientific notation to standard notation. What we need to look at here is what is the exponent of the power of 10. So in this case, my exponent is 12. So since my exponent is positive, should my number be greater than or less than 1? So should it be a whole number, or should it be a positive number, or should it be a number that is less than 1? And I shouldn't say positive number. I'm saying should it be bigger than 1, or should it essentially be a decimal? So in this case, since it's positive, I know it should be greater than 1. Okay, since this is 10 to the 12th, I'm multiplying by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I am actually multiplying by this number. Okay, so I'm taking 4 and 18,549 hundred thousandths, and I am multiplying that by this number. Okay, but instead of doing that, we know that since we are multiplying by this number, multiplying tells me that my decimal moves to the, multiplying by a power of 10 means my decimal moves right. So it's going to move to the right 12 spaces. So I'm actually going to write this again up on top. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I move my decimal point to the right, and I know I have to move it 12 spaces. So since I'm moving it to the right, I add the zeros at the end. So 1, 2, 3, how many did I add? I added 7, 4, 5, 6, 7. My decimal is now down here, and I put in my commas. And that is my new number. So my new number is quite long. And so the reason that we use scientific notation is so that way when we're referencing this number, and so scientific notation does imply to you that it's used in science quite a bit, because think about science, you're working with atoms, which have very, very small masses. And there are so many of them. So when you're working with those large quantities and small masses, we like to use numbers that are written in scientific notation, like this, to make it a little bit less cumbersome when you're writing stuff out. Because can you imagine having to write this number over and over and over again? And this isn't even that bad. Okay, so now again, we're going to go through the steps and we are going to look. What is the exponent? The exponent in this case is -6. So since it is a -6, I know that my number should be less than 1 because the negative tells me that this should turn into a fraction, which we know turns into a decimal. So this number should end up being smaller than 1. So there should be a 0 on the left side of the decimal when we're all done. So I know that since I have a negative exponent that I'm dividing by, and I have 1, 2, 3, 4, 5, 6. So I'm dividing by this power of 10, which happens to be a million. And I know that because 10 to the 6th power, regardless of positive or negative, means 1 with that many zeros, so 1 with 6 zeros, and the negative tells me that I'm actually dividing. Okay, so since I'm dividing, I know my decimal point should move left. Okay, and so I'm going to move it to the, well, and they didn't change numbers, so 2, 5, 6, 8, and these become zeros. We'll just do it this way, so 8, 6, 5, 2, and I'm moving it to the left 6 places, so 1, 2, 3, 4, 5, 6. So each of these becomes a 0. And so this number written in standard notation is 0.0000000. 2, 5, 6, 8. So in this case, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions, 10 millions, 100 millions, billions. So this is 2,568 billions. Again, not that bad, but can you imagine writing this over and over and over, or even writing numbers that are tinier than this? So remember, we talked about when you have a negative exponent, so 10 to the negative 6th actually means 1 over 10 to the 6th. So 1 over 10 to the 6th is the same thing as saying, so multiplying by 1 over 10 to the 6th is the same thing as dividing by your 10 to the negative 6th. Okay, so that's where the division part comes in. You're not actually changing this right here. You're not changing that to division. This just means that by multiplying by the negative exponent, that changes the multiplication to division. So that changes the direction that your decimal is going in. All right, so we're going to try. So we're going to take 4 times 10 to the 5th. I know that means I move my decimal, so 4, and I move it 1, 2, 3, 4, 5. So my answer is 400,000. So 8 3/10 times 10 to the negative 4th. So the negative 4th means that my answer should be less than 1. So that means that my decimal is going to move to the left 4 places. So 1, 2, 3, 4. So that means my answer is 0 and 83 tenths, hundredths, thousandths, 10,000ths, 100,000ths. Say that 10 times fast. So here I have 6 41/100ths times 10 to the 3rd. The positive exponent means that my answer should be greater than 1. I move my decimal 3 places to the right, so 1, 2, 3. So my answer is 6,410. Here I have 8 456 thousandths times 10 to the 7th. I know that this means my answer should be greater than 1, and I have to move my decimal 7 times to the right. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4 zeros get added at the end. So 8, 4, 5, 6. And then I add my 4 zeros. So 1, 2, 3, 1, 2, 3. I get 84,560,000 as my answer. All right, so again, the negative exponent tells you if your answer, so negative exponents equal a number in standard form that is less than 1, and positive exponents equal a number in standard form, so I'm going to put SF, that is greater than 1. Right, so if I give you a number in scientific notation, you should be able to tell me without extending it out if it's greater than 1 or less than 1 just based on the exponent. And on that same token, if I give you a number in standard form based on whether or not it's greater than or less than 1, you should be able to tell me if my exponent should be positive or negative. So you should be able to go back and forth with these. All right, when you're comparing numbers in scientific notation, so we want to know which animal has the larger weight. So we have the whale shark, who is 4 times 10 to the 4th pounds. And you have the dolphin, who is 2, times 10 to the 2nd pounds. So without extending this out, we want to look at which one is larger. Well, the first thing you need to look at is your power of 10. Since the whale shark has a greater power of 10, this is going to be your larger number because this is going to extend out further. So the larger the power of 10, the larger the number. Okay, so because this turns out being 4 times 10,000, and this ends up being 2 times 100. Well, you know just by looking at it this way that this one is going to be larger. So the first thing that we look at when we are comparing numbers, so just deciding which one's smaller or larger, we look at the power of 10. And then second, if that doesn't work, you look at, so if the powers of 10 are the same, you look at the other number you're multiplying by. You look at your other factor. Okay, and I'll have an example of that one coming up. So when you're comparing numbers in scientific notation, they also might say how many times as great or how many times greater are the weights. So the first thing that it's still the same, we have the dolphin and the whale shark. So the first thing you're going to compare is your values between 1 and 10. So we're going to compare these two first. And we know that the 4 is 2 times as great as the 2. Then you compare your powers of 10. Now this is where you have to be careful. Okay, so your second piece is to compare your powers of 10. We like to look at this and think, ooh, it's 2, but that's not the case. It is not 2. Just because 4 is 2 bigger than 2, you have to look at what this actually means. So 10 to the 4th actually means 10,000, and 10 squared means 100. Okay, this is actually 100 times bigger. So 10 to the 4th is 100 times bigger because it would take 100 times 100 to get you to 10,000. So it would take you 100 times 100 to get you to 10 to the 4th. Okay, so you can't just look at the exponents, you have to look at what they actually mean. Another way to look at it is that 4 minus 2 is 2, so then your number has to have 2 zeros. So then what we do is we look at it and we say, okay, well, we have the 2, so we know that the base, I don't want to say the base, we know that our numbers between 1 and 10, that the 4 is 2 times greater than the 2, so that piece is just 2 times as big. And then we're going to multiply that by how much bigger our exponent is. So you take those two and you multiply them together, and you find that the whale shark is about 200 times bigger than the dolphin. And maybe we'll say heavier. Okay, so first you compare the numbers that are between 1 and 10, and then you compare your powers of 10. And then you multiply them together to figure out how many times heavier the numbers you're comparing are. So how many times heavier your larger number is than your smaller. Because we decided already that the whale shark was larger than our dolphin. Okay, now we're looking at the population of the United States and Maryland, and we know that those are the two of them. So we have 3 and 7/100 times 10 to the 8th, and we're comparing that to 5 and 7/10 times 10 to the 6th. Since this is the larger power of 10, we know that 3 and 7/100 times 10 to the 8th has to be greater than 5 and 7/10 times 10 to the 6th. So we know that the U.S. population was larger. Even though this 3 is less than this 5, that doesn't matter because you first have to look at your power of 10 because this is going to turn into a larger number because it's being multiplied by a larger power of 10. Okay, and as a quick example, let's say that they're both the same. So let's say that we had times 10 to the 6th times 10 to the 6th. Since they're both the same, then you would compare your other numbers. So when your powers of 10 are equal, you compare the numbers that are between 1 and 10. So if these are the same, so again, step 1 would be to compare these. Step 2 would be to compare your number that is between 1 and 10. So first the powers of 10, then your other two numbers. So we're checking place values. So when we compare numbers, we always compare place values. Well, this times 10 to the 8th power is going to put 3 in a greater place value than this 10 to the 6th power is going to put the 5 in. So that's why this is larger. Okay, if you extend them out, the place value, this number gets to a further place value than this one does, and that's why it's larger. If they extend to the same place value, then you have to look at, okay, well, if they extend to the same place value, 5 is bigger than 3, so it has to be larger since they both end in the same place value. Okay, now here, this is a little different. So here I have these two populations and I want to compare them. Well, looking at this, I know that 3 and 7/100 times 10 to the 8th is larger than 5 and 7/10 times 10 to the 6th. So when I compare, it's going to be a little bit different. So I know that to go from 8 to 6, so 10 to the 8th, is 100 times greater than 10 to the 6th. Okay, and then if you look here, this is about, you can look at these and say, okay, 3 and 6. So we're not going from 3, so when we go from 3 to 6, though, our value is actually going down. So you're not actually going to, so this is about 2 times greater, but this time, since the numbers are being compared downward and our number here is smaller than our number here, you're actually going to divide. So you have your 100 times and you're going to divide it by the fact that this gets, so the fact that this gets smaller by about 2 times means that it's only about 50 times greater. So you can look at it one of two ways. Since this goes down when we compare, since this goes down, it goes down by 100 times, but then this number also goes up. So that down means that there's going to be some division in there. So you really want to look at, okay, how do I get from my one number to the other number? And since to go from 3 to the 5, or essentially 3 to 6 if you round, I would go up times 2, but I would divide by 100. I have to put those things together and say, okay, well, even though I'm multiplying by 2 to go from 3 to 6, I'm dividing by 100 to go from 8 to 6. So to put those two things together, I say, okay, well, it's not going to be 200 times larger. It's only going to be 50 times larger because of the fact that my value here in my exponents goes down. Or you can look and say that when I go from my smaller exponential form to my larger exponential form, yes, my power of 10 goes up, but that other number, so this number goes down. And when that happens, you divide these two numbers to find your answer. So it's 50 times as great. Okay. I know this is a little bit confusing. Just take your time and work on it and work your way through it. This is something that is more of an extension that I want you to be aware of. What you really want to make sure that you have down pat is this, where you compare using the exponential form and then your numbers that are between 1 and 10. Okay, and you have a couple of you-try problems. As always, if you have any questions, be sure to write them down or email me so we can go over them in class.